Hello, this is Adam Ward, and today I'd like to talk to you about example 8.3 in the Surface Water Quality Modeling textbook from Steve Chopra. In this problem, we're considering the Saginaw Bay Lake Huron system. We're given a whole table of information from Chopra. Earlier in the chapter and in lecture in our class, we derived the diffusion flow, and we're given a settling velocity for phosphorus of 16 meters per year. Our objective is going to be to calculate the steady state concentration in both the bay and in Lake Huron. And so conceptually the model looks something like this. We've got a bay and a lake. We've got a discharge from the bay to the lake, and we've got diffusion shown in red between the bay and the lake. Settling out of both of those, an independent load into both of those, and discharge out of Lake Huron through the chain of lakes, Huron discharging into St. Clair, which we looked at in a previous example. So for our solution scheme, the first thing we're going to do is write the mass balance for Lake Huron, and this looks fairly similar to the same mass balance equation we've seen in the past, where we've got the rate of change of concentration on the left-hand side and all of our source and sink terms on the right-hand side. And we'll also write that same equation for the Saginaw Bay. Again, accumulation is equal to sources minus sinks. One thing to point out here as we're working with diffusion for the first time is the order of these concentrations that are shown in the terms indicated with the orange arrows switch. And as we discussed in class, that switching of order prevents us from losing mass in the system. It means a loss out of Lake Huron is a gain into the Saginaw Bay, or a loss from the bay becomes a gain into Lake Huron. We achieve conservation of mass, and it lets us push from high concentration to low concentration, whichever way that gradient would change. Now, from those two equations, we can make a few simplifying assumptions. One is that we're looking for steady state concentrations, so the time rate of change for concentration is 0 in both cases. So we'll go ahead and zero those out and reorganize our equations a bit. Now, as I write out equations for the loading into 1 and the loading into 2, you can see that I've gone ahead and grouped terms so that all the coefficients multiplied by concentration 1 are together and all of the terms multiplied by concentration 2 are together. The reason I've done so is that this lends itself to the matrix solutions that we discussed in previous lectures in our class. Now, we've got a system of two equations, we've got two unknowns. There are a few approaches that we can take here. Of course, option 1 is to go through matrix inversion and actually solve the systems of equation that way. For a system of two equations, Chopra has provided us with some shortcut solutions, just algebraic manipulations that can help us get to the answer. And so we can explicitly calculate concentration 1 and concentration 2 using the equations that are shown on the slide here. And so that's the strategy we'll take here, since we've covered matrix inversion already in class. So in order to do this, we want to go ahead and calculate all of the terms that I've identified in the green text on this slide. So on the next slide, we'll calculate each of those forcing terms. And so A11, or the response of 1 into a load in 1, we've got the discharge, settling velocity times the area, and the diffusion flow. For A12, we've got diffusion flow, and we've got the outflow. A21, the only term we have is diffusion flow, and for A22, then we've got several terms again. We've got outflow, settling, and diffusion to consider. So with all of the A's calculated, the only thing we're missing are the loads. Loads were given to us in table 8.1 in this problem. So loading into the bay and loading into Lake Huron, W2 and W1 respectively. Now, with those data, we've got all of the values that we need to plug in. We've got the two equations to solve for our two unknowns. You can do the mathematics on your own, and we should come up with calculations, or concentrations, of 4.44 milligrams per cubic meter in Lake Huron and 28.36 milligrams per cubic meter in the Saginaw Bay.